All right, so today we're talking about factor analysis, which is by far of all the topics we talk. I know I say this a lot. I love this topic. This one is actually by far my favorite. I mean, obviously, it would have to be if I went, went to UCLA to get a degree in measurement and psychometrics, mainly because of my love of factor analysis and other things, latent variable. So, I mean, factor analysis is, when I first learned about what it was, it truly fascinated me. And I think just the idea of latent variable modeling and measurement theory in general is awesome, because I remember going through other stats courses and always feeling like there was something missing. As we created composites and compared groups or did prediction, I always thought that wasn't the way I sort of saw how variables related to each other. And with factor analysis and later on, like structural equation modeling and other latent variable modeling, it was like it finally fit my way of sort of seeing how things, were fitting together. So this is sort of, this particular topic is sort of a precursor to next semester for some of you that are taking Psy524. It's really an entire course built around this idea of sort of factor analysis and latent variable modeling. If you think of latent variable modeling as sort of the umbrella term that people use a lot, where factor analysis is just one type of latent variable model, and there's other types like item response theory is another latent variable model. So we're going to talk more about this stuff a lot next semester for those of you who take Psy524. But for today, let's talk about how we can use this to our advantage. We're going to talk about factor analysis as like a specific analysis. We're going to go through specifically something called exploratory factor analysis. But in general, again, if you think about this as a way of trying to identify things that we're trying to measure in a more sophisticated way than we typically do. So oftentimes we'll get a scale, has a bunch of questions, we add them together, and we create a composite, and we use that as a dependent variable, a predictor or something. And this is a way of taking the stuff we already did in canonical correlation and in discriminant function analysis, and just taking it a bit further and being a little more flexible about how it's applied. So let's talk about it. So what is factor analysis? Most people, when you ask, like you read in a textbook, what is factor analysis, they'll tell you it's a data reduction, pattern identification sort of process. We have a bunch of data and we want to reduce it, right? And in that way, it actually sounds sort of lame. It's like, all right, well, I got a bunch of data, I want to reduce the data. It sounds, it's a means to an end, especially if you have lots and lots of variables. But it doesn't sound super exciting. It's not very sexy. It's like, oh, let's just reduce data down because I got too much of it and I can't handle it. It's like, it's just, I don't know. The pattern identification part of it is a little bit more interesting. It's like, all right, what kinds of patterns are there? What variables seem to go together, cluster together, and what variables seem not to cluster together. But this data reduction pattern identification definition of factor analysis really sort of misses a ton of what really is going on, and it really sounds sort of atheoretical. Well, I happened to stumble across all these variables. I don't know where they came from. They just appeared. Now I want to know if there's patterns in them, which it's very unrealistic. You collected the data, the variables you're collecting. There's really more to it than that. It's not this black box sort of secret thing. So that's why I like to describe it more in these ways. Really, it's part of the sort of general sort of measurement theory. It really is used a lot in sort of what's called psychometrics, which is a fancy term for psychological measurement. To do lots of things, to create scales. If you're trying to create some new scale to measure whatever it is, to measure depression, to measure ethnic identity, to measure, you name it. It has gone through some process that includes factor analysis or something like factor analysis. And I say that because it may have gone through something called principal component analysis, which is really a very close sort of sister, brother of factor analysis. It may have gone through item response theory, which is a little bit more computationally intensive and it's a little more modern than factor analysis, but it's the same basic principles. And really what we're trying to do is create, just like with canonical correlation, create these smart composites. We actually want to make composites that actually weight the items more, that are more useful or relate more to the scale, and downweight those that aren't that useful. It actually does more than that too. As we're creating these smart composites, it's actually able to separate out parts of the variables that are useful and parts that aren't, and sort of we use the useful parts and sort of throw out the non-useful parts. So it's really, it's not just about scale creation, but in a bigger way, it's about test theory, it's about test development, and it's a way of looking at sort of scale and item reliability. So you've probably, at least in some way or another, had some experience with like Chromebox Alpha, which is a way of looking at whether or not items are internally consistent. And in that way, Chromebox Alpha and factor analysis are doing, in general, the same type of thing. Or do these items go together? With this idea that if I have 10 items and they're all measuring the same thing, they're all part of some underlying scale, some underlying construct like depression or something, then all those items should relate to each other because they're all related to the same one scale. Factor analysis has that same sort of assumption. It's just the way that factor analysis goes about is a little more complex than Chromebox Alpha, and it's a little more flexible than Chromebox Alpha, but it's the same basic idea. So we can look at sort of scale versus item reliability in this way too. So when people say it's a data reduction method, the reason why is because oftentimes you're faced with things like this. This is many years ago, I used to use this thing. It's called the math anxiety scale, and I would give it to students in like my intro stats course to just to see if these things sort of predicted outcomes. It had a lot of weird things. I stopped sort of using it because the prediction was sort of inconsistent. Sometimes people who have high math anxiety ended up doing better in the class than others. Sometimes people that had low math anxiety ended up doing better. And the reason why that is, I think, is because whether or not you sort of use that anxiety as a sort of motivator. So sometimes you need enough anxiety about it to sort of push you to do, to want to do well, to want to study, to want to perform in the class. And sometimes that anxiety can become overwhelming, and therefore it sort of kills your ability to do stuff in the class. But so it's not a very consistent predictor of sort of outcomes. But it has 24 items, and these are the correlations between those 24 items. And to try to figure out if there's anything going on in here, are there patterns? Are there certain items that go together? Are there clusters of items that go together? If we were to do this, it's not only is it complex, but it becomes almost impossible to really try to figure out what things go together and what things seem to be separated from other things in any real, consistent, applicable way. So when people talk about factor analysis being a data reduction method, it's because we take something like this huge 24 item, 24 by 24 matrix here, and we can use factor analysis to identify patterns and trends and group items together that go together, and to separate items from each other that don't seem to go together. And we can sort of cluster them into subscales, or we can figure out that all 24 of these items really fit under one general construct, like math anxiety. We really need one construct to explain all 24 items, but oftentimes with 24 items, it's probably not going to be one factor. It's likely going to be a few. Okay, questions so far? Since I can hear you guys, so if you have questions, just let me know. So the reason why I say it's this idea of sort of creating these sort of smart composites is because what we typically do in when we have a scale. So let's say I had a 6-item depression inventory. It's called like the Ainsworth depression scale or something, right? What we typically do with that is, we'd have these 6 items here, and usually the instructions are something like, let's just add them all up. So I'm going to take 1 times this item, right, and I'm going to sort of add that in, 1 times item 2, 1 times item 3, and I'm going to add in all of those items together, and I'm going to use 100% of each item and add them all together. The problem with that is that, and we talked about this before, is that's assuming that all items are equally important. That's one problem with it, right? So if you're looking at these items, an item like I feel depressed versus, I eat more or less, or let's say I eat less than I used to or something like that, the eating item is going to be less directly related to depression than something like I feel depressed is. But in creating these composites like this, we ignore that. And we say, well, they're all equally important. We're just going to add them together. The other issue with that too, and something we didn't talk about before, is that when it comes to sort of measurement theory, each of these items, right, is not completely 100% reliable in measuring anything. It's going to have some usable variance and it's going to have some error. And when we add them together in this way, we're actually not only adding up the item's usable variance, but we're also compounding all the error. So now this depression factor, or this depression construct here, has all the error compounded into it too, making it sort of a messy, error-prone sort of composite. With factor analysis, one of the things that we're able to do is to figure out, just like with canonical correlation, is we're actually able to figure out things like loadings and figure out ways of sort of differentially weighting items. Let's figure out, all right, well, what's the relative importance of all these items? And let's use that to combine it so that we're actually sort of up-weighting good items, down-weighting bad items. I don't mean bad in the sense of they don't relate, because they have to relate to some degree or else we would drop them. Like if item number 6 had a 0 loading, like it didn't relate at all to depression, why would we keep it in there? We'd probably drop it anyway. So it's not that item 6 doesn't relate, it just doesn't relate as well as another item. So this one will get a lower weight, a lower loading, and other items may get higher loadings representing their relative importance to that particular construct. All right, what's not shown in this is that by doing that, I'm actually weighting, let's say I'm weighting item 1 here by some thing, because I have it in this way. It's like this is a way of, notice all the arrows are going towards depression. It almost looks like a little half circle here. Those are all arrows that are dead-ending into depression. What's not being shown here is that by doing this, I'm also able to separate out the error. So if I'm only using some part of item number 1, some portion of it because of the weight, there's a portion of it that I'm not using, and we're hypothesizing, theorizing that the part that's being left out is the part that's unrelated to depression. So we're actually able to get rid of some variance that is either just specific to item number 1, or that is just noise and doesn't relate to anything. So we're actually able to get rid of that. So when we add all these together, depression should be cleaner. It should have less error built into it and be a cleaner, nicer factor or composite when we actually put them all together and put it all together into a composite using these weights. Okay? So that's the idea of sort of creating smart composites. We're actually able to sort of weight different items, get rid of some noise and junk that the items bring in, and then add them all together and get a nice clean construct. So what is factor analysis? All right, so oftentimes factor analysis is, so I'm gonna do the same thing that people do a lot. Is I'm gonna refer to factor analysis as this whole sort of family of things, which includes principal components analysis. So when I say factor analysis as a general term, I'm really including principal components analysis in there too, because it's really all part of the same sort of idea. It's just that the mathematics and some of the assumptions are a little different between a true factor analysis like principal axis factoring versus a principal component analysis. But the goal is sort of the same, but you will get some different results and things depending on what you use. And they just have different assumptions about your data. The idea is that in terms of data reduction, we want to take many variables and explain them with few factors or components. This is like canonical correlation. We want to take a bunch of items, we want to combine them down into 1 or 2 or a few different dimensions that actually can help to explain how the items relate. So correlated variables are grouped together, and other variables are separated out that aren't related. And what we should get is sort of few clusters of items that sort of relate to different factors. And this is either done as just like a descriptive process. So when I say descriptive, I mean, this is really more reflective, I think, theoretically of a principal components analysis. Let's sort of figure out what the weights are. Let's combine these items together into a composite with really no theory or further sort of mathematical complexity to it. Let's just sort of like a canonical correlation. Let's just figure out what items are more or less related. Use those weights to combine them together, create a smart composite. In this case, we're going to call it a factor score. If it's a factor analysis, sometimes they call it a component score if it's a principal components analysis, but we're going to create a score that represents this single thing as a combination of all these other items. So to me, it's either descriptive, which is I'm saying like is a principal components analysis, where it just sort of describes how the items go together, or it is reflective of an underlying theory. And that's where sort of factor analysis comes in, where you're actually theorizing that there's a latent variable, this construct that is driving the responses to those items, and you're trying to sort of identify what those latent variables might be. Right? So principal components analysis is more descriptive. It's a way of combining items together. And then fact analysis is more theoretically driven, and it really is trying to identify what the underlying factors are that are driving items. And a bigger thing to me is this idea too, it provides operational definitions for latent variables. This is where it gets to the psychometrics. If I want to define depression, factor analysis helps me figure out a way to define it. If I have a new construct like, I don't know, let's say I'm trying to develop a coronavirus anxiety scale or something like that, right? It's specific to this, fears around this particular virus that I want to develop. It's brand new. It's never been done before. I can take other types of scales and sort of tweak them or something, or I can develop my own scale and then use the items and the factor analysis as a way of operationally defining how that is measured and if that measurement of that particular type of anxiety is valid or at least reliable. Okay. So some of this stuff, if you notice the slides that you have include there's like 90 something slides, and I'm only going to cover about I think 60 of them or something less than that because there's stuff I try to cut out to reduce things down. And part of that is I talk a little bit about classical test theory and this true score model and stuff, which really comes back to sort of this idea of operationally defining. So it's in this one topic, like factor analysis, where you get this a bunch of topics coming together. You get sort of psychometric theory, you get things like research methods, like in 692, things about operational definitions and how we operationally define things, plus the statistics that are sort of behind it all, sort of all come together. So it's like to get a real true full treatment of what factor analysis is and what it does, you really need to take a class on measurement theory, which we have. It's like 427. And in this class on sort of how to analyze and sort of how to deal with it, and then in sort of a more advanced class on research methods like 692 to get a full picture. So I've taught 427 and 524 before, and the way I handle the factor analysis was a little different, and I focused more on the sort of the theory and how it relates to classical test theory and stuff. Where in 524 we focused more on the sort of the application, and it's really sort of two sides of the same story. And so it's to get a full picture. So I try to include some of that stuff in the slides that you have. And so if you're interested more in sort of what the true score model is and classical test theory and how it relates to factor analysis, you can do a deeper dive and sort of look up some of that stuff, and you can find that there's really more to it. But we're going to focus on the application part. So if you think about, it's like I said, oftentimes people talk about factor analysis as this umbrella term that really includes both principal components and something called common factor analysis. Now, common doesn't mean like ordinary. It really means that it should be called like common variance factor analysis. But it's this idea of the actual like exploratory factor analysis sort of falls in here, like down here is a type of factor analysis, and principal components analysis, though the goal is the same, sort of gets there under different sort of simpler assumptions. So these two things are very similar, and sometimes when you do them, you may not get the same results depending on your data and some other things. But they are sort of doing things, very similar things under different assumptions and with different underlying theoretical sort of beliefs about the data. And with common factor analysis, the common factor model, there's two types, exploratory and confirmatory, where exploratory is what we're going to talk about in here, and confirmatory is a little bit more computationally intensive and requires a little bit more theoretical background in terms of what your beliefs are about your items and your scale. And this is going to be more the primary focus of the 534, of the latent variable modeling class, is how to do a confirmatory model. because you need to go either outside of SPSS or use SPSS's sort of accompanying sort of software called AMOS, or go into some other programs like R or EQS or M+ or other things that actually do confirmatory factor analysis and structural equation modeling, latent variable analysis type stuff. So we're here. We're going to talk about both of these sort of in general, but I'm going to focus more on common factor analysis and sort of doing it exploratory through SPSS. All right. So what's the difference? Just to sort of clarify, like in exploratory factor analysis, we're trying to summarize data by grouping correlated variables together. It's more of an investigation of sort of measured variables and how they relate to theoretical constructs. It's usually done earlier on in research. It's usually when you're developing a scale and you're trying to find out if the items sort of go together in a way that makes sense and how they really are hanging together and how people are responding to items in a consistent way. And it's what we're going to talk about in here for the for the remainder of for this class and the next lecture. Confirmatory factor analysis, in a sense, is doing the same thing, but it requires that you know a little bit more about the data. And because you're confirming the factor structure, you got to know what the factor structure is before you actually do a confirmatory factor analysis. So it's more advanced. You got to know the factor structure, or at least have some theory about how the items should go together. It's a way of sort of going from exploratory. Once you sort of identify what this factor structure is, you can then try to generalize that factor structure to new data by confirming it. So I find that there's a 3-factor structure for a set of items I have. Well, I can then go in confirmatory and try to confirm that 3-factor structure on new data to see if it actually does fit and really does explain and generalize to new data on the same scale. This is often tested through things like structural equation models or latent variable models or whatever term you like. And we're going to talk a lot about that in Psy524, the latent variable modeling course. That's going to be basically the foundation for most everything we talk about in there. I should say this too, the confirmatory factor analysis, not only is it confirmatory and you get into the factor structure, it'll actually allow you to, if you're doing confirmatory factor analysis through something like a latent variable or structural equation modeling approach, it allows you to do more things. Like you can actually take one factor and predict it from another factor. You can actually, you can take the idea of testing factors sort of beyond what is done in exploratory factor analysis. All we can really do here is identify if the factors are there, and then figure out if they're either orthogonal, like independent, or correlated to one another. We can do that here. Here we can do that and a lot more. So it allows you to test more complicated. There's multi-level structures. You can test for latent variable mediation and moderation and all kinds of crazy stuff you can do in these confirmatory models that you can't do in exploratory. At least you can't do easily in exploratory models. All right. So we're going to spend a lot more time next semester talking about this. So today, focusing on this, and this is sort of like baby steps. Let's get into sort of the exploratory factor analysis, and then you can, then we'll spend more time next semester doing this. So here's the thing, little story. It's funny that the first conference that I ever went to present a poster was at a Western Psychological Association conference, and I went there to present an exploratory factor analysis of a few scales that my mentor at the time had been using. Was like, and you've seen a lot of these. It's the classic and racial climate, the ethnic identity, all those items. They had taken these intact scales and they had cut a bunch of items out to make them shorter because they were all a little too long. And so we wanted to see if the factor structure still held after they cut a bunch of items out. So that was my first presentation. First time, taking a poster to a conference was doing an exploratory factor analysis of those scales. And it just happened to be, it was interesting. It was a WPA that was held in Hawaii, Maui, Hawaii. So the first conference I went to present was in Hawaii. It was pretty cool. It was a very well registered conference, not very well attended, however. Most of the things were pretty empty because no one wanted to go to the conference when there was beaches and all kinds of cool stuff around. Anyway, I had my presentation was like 8 a.m. or something like that, and I think I ended up presenting it to my neighbor who was presenting her poster, and she presented hers to me, and that was it, because no one came to any of the poster sessions. Yeah, especially not at 8 a.m. in Hawaii. Anyway, okay. So in general, what are the steps to doing a factor analysis? The first step should seem rather obvious. You gotta identify some items. You gotta, you gotta figure out what those are. Selecting and measuring a set of items in a given domain. So you got to go out, identify items you want to use, identify what scales you're trying to collect. Go out and collect data from, and we'll talk about this later, but a fairly large number of people. Like you can't just do 30 people and then do a factor analysis. It's got to be quite a few people, hundreds typically. And then you're going to do some data screening, and the data screening really has to do with the fact that all of this is going to be based on a correlation matrix. So anything that affects a correlation is going to affect a factor analysis. So your items need to be continuous, normally distributed. They need to be linearly related to each other. They need to be, you really can't have any outliers. Any outliers that would affect the correlation would affect factor analysis. So you got to screen for those types of things. So the first step in an exploratory factor analysis is what's called factor extraction. Right, so that's just a fancy word for saying let's identify how many factors are in the data. How many different underlying factors do we need to explain the relationships between the items? And once we sort of come to some decision about the factor extraction, then there's something called factor rotation. So factor rotation really comes down to trying to manipulate the factors in a way so that it's easier to interpret what they're doing. And that sounds like cheating in a way, but it's doing a mathematical rotation to ease the interpretability of the factors, and to try to find something that we'll talk about later called simple structure. So it's trying to identify if that's possible by rotating around and trying to find the best solution to your extracted factors. And then once you sort of have that, you can then go to interpretation, which in some ways might actually be the most difficult part. It's the non-mathematical part. You're sort of looking at the loadings, trying to figure out what items seem to go with each other, and then trying to identify what those items are measuring. So if it's some subscale of a larger scale, you have to identify what sort of is the subscale that those items are trying to address. And then even then, once you sort of, if you found a nice clean factor model that seems to fit and you can actually interpret it pretty easily, there's still a lot more to go. It's like if you just do that part, it's not like you can just go and like publish a scale just from that. You'd actually have to do some validation and further sort of reliability of the measures. And that comes down to I think you guys in 692 talk about validity and things like convergent, discriminant validity. It really comes down to sort of then validating those scales for validity. In fact, that makes no sense. Validating for validity. Anyway, so to validate the scales to see if they actually relate to other similar types of scales, and that they're different or discriminating from scales that shouldn't be related, and so on and so forth. And then looking at sort of further reliability, being able to generalize and be able to take your factor structure to new data, get similar results, so you see that it sort of generalizes and it is replicable across things before you really come down to a final sort of structure. All right, so there's two questions right there, right? So one is, are the loadings for a factor analysis sort of developed in a similar way as they are for canonical correlation? And then two, is the only difference that we've identified the sets and stuff in a canonical correlation, or in factor analysis that's not the case. So for the first question, the loadings are interpreted the same way, right? It's the same basic idea that once we identified a canonical variate, we then look to see how well each item relates to that variate by looking at loadings. The same thing with the factor analysis. We're going to develop factors. They're going to be we're then going to sort of correlate each item with the factor and find out how correlated they are, and that's going to tell us the relative importance. Those are loadings. They're interpreted the same way. Loadings are the same. With the second question, the answer is more or less yes, that with With factor analysis, we're not starting off with identifying two different sets of items. We're starting off with one giant set, and we're not trying to. Our motivation for factor analysis. So let me back up. In canonical correlation, what was the main driving goal in canonical correlation? Right. So we had, two variates on both sides, right? And they had their items, whatever that loaded on them. But the whole driving goal was this correlation. This correlation in the middle was the main attraction, right? We were trying to figure out these loadings or these weights and loadings to try to make this as large as possible. So we had a goal that we were trying to direct towards, make the correlation between the variates as big as we can. Right? We don't have that with factor analysis. Factor analysis, the goal is not to try to make them correlate, not anything. It's just to try to identify patterns. There's no sides. There's no. So if you think about trying to do a canonical correlation, it's mathematically the same. We're going to use the same eigenvalue, eigenvector deconstruction. It's just instead of trying to do it on two different sides simultaneously, we're just treating everything as all one big set and trying to figure out what the patterns are using that same eigenvector, eigenvalue deconstruction. And we don't have this goal of correlating them, that's there. Actually, a lot of people, the goal is to try to find factors that are not related, but they're actually sort of separate, independent factors. So we don't have this goal, and we don't have the sets separating them out. So with canonical correlation, you actually have to have a preconceived sort of idea that there are two different sets or two sides to this, where with exploratory factor analysis, there isn't. All you have to do is, I know all these items are measuring something similar, and I want to explore, what the items are doing and how they are relating to one another to try to come up with the best sort of reduced solution for those numerous items that we have. That make sense? Yeah, so with principal components and exploratory factor analysis, it's actually the exploratory factor analysis is actually computationally more intensive. It's okay. So really, in the grand scheme of things, so the question is, how are PCA and EFA different from one another? And I had mentioned that EFA is more computationally intensive and stuff. Really, it's confirmatory factor analysis on one end is like the most computationally intensive. And then you got exploratory factor analysis, something like principal axis factoring or something, or maximum likelihood exploratory factor analysis, sort of in the middle. And then principal components analysis is sort of on the lower end in terms of computationally intensive. There's lots of reasons, but the main thing is that principal axis factoring and confirmatory factor models, that kind of stuff, are iterative. They require you to put information into the model. It runs the model. You get data out from the model. It puts the data back in again, and it keeps running it over and over again until it converges, which makes it more computationally intensive. It actually may go through 30 iterations before it sort of converges and you get a solution. Principal components analysis is a one-shot sort of descriptive thing. It says, what's the, how are these items related? It spits out some stuff. That's it. And it's really seen as being more driven as a descriptive, like, okay, well, how are these items related to each other, without really trying to develop the underlying theory that's driving why they're related. It's just saying, look, these 5 items relate, but we don't know why. So it oftentimes will overestimate the number of underlying factors or underlying constructs or components there are. It has a tendency to do. People tend to use principal components more early on to explore how items are related, and then move to exploratory factor analysis once they sort of trimmed off items that don't seem to be working, and then once they have a set of items that seems like they work and work in factor analysis, then they move to confirmatory models to then confirm that those items actually work the way they think they do. So you can think of that. It's not always that way, but sort of seen as like principal components a little more early on, a little more exploratory, a little more descriptive. Exploratory factor analysis, while still exploratory, is a bit more theoretically driven. And then confirmatory models is completely theoretically driven, and you're sort of testing what the theory actually applies to the items. So, and I'll talk a little bit about what the assumptions are differently. One, with exploratory factor analysis, we're trying to identify what the common variance is from the start. With principal components, it actually assumes that 100% of each item shares variance with all the other items. So it's almost like going back to that was a big sigh. Anyway, it's like going back to here. Principal components almost sort of starts with this sort of idea that 100% of each item relates to this factor, and then it cycles through once to tell you, okay, well, how do we adjust these, to be something more like these B weights? Exploratory factor analysis starts with this idea that only part of the variance of each item relates to the factor, and then cycles through to try to identify how much that is. So what that does is it tends to mean that the loadings on the principal components tend to be much larger. We tend to identify more factors than we do over here because it's trying to use more variance. So we'll come back to that more in a little bit as I talk a little bit more about the differences between factor analysis and PCA. Did that answer your question, at least partially? Mm-hmm. All right. Moving on. Let's talk about over here. So these steps: measure some people using your scale, do some screening, extract, rotate, interpret. Likely you get to extract, rotate, interpret, and you start over again. Because when you get down to here, you realize, crap, I can't interpret anything. These factors are messy. They're hard to interpret. So we're going to clean things up, go back, do some of this stuff again. And then once you sort of have something you're happy with, then there's sort of further validation and do some more reliability and other types of testing. All right, so what are the general questions? Questions like, how many factors do I need? Right? I have a bunch of items. How many factors do I need to explain those items? That's the main question in exploratory factor analysis or principal components, is how many components or factors do I need to adequately describe the data that I have? How many interpretable factors are there is often the main question. What do they mean becomes a more complicated question, and you saw that somewhat with canonical correlation, where when we saw loadings between items, we were trying to figure out, okay, well, how do we interpret how these items on this side relate to this side, and you got to look at the loadings, and you got to figure out how that works. So it's more of that same kind of thing, where we're trying to look at the loadings of items to figure out how they go together, and then figure out what exactly that thing is measuring. Then we start asking questions like, well, all right, well, if we have these factors identified, how good of a job are they doing at actually capturing the variability in the items? So there's this sort of what percentage of variance in the data accounted by the factors. And we saw that somewhat with canonical correlation as well, with what they call like redundancy analysis. How much are the items redundant with the variates? Same thing, we can actually look at how much variability in the items is actually explained by the factors, and be able to look at how good a job the factor analysis is doing at capturing the items. We can sort of rank order factors in terms of what factors seem to be accounting for most variance down to the least. How well does the factor structure fit a given theory? So that goes beyond sort of interpretation. So now we're trying to look at the items and figure, okay, well, what do these items have in common? And, sort of why are they on the same factor together? And then looking at saying, okay, well, does that seem to match the theory that is sort of beyond, behind the particular scale? And then a really important part too is, well, because it's a latent variable and because we're only able to measure people on individual items, what if we were able to measure people's scores directly? So if we're trying something like depression and you wanted to measure their level of depression directly, is there a way to actually use the factor model to create a factor score that actually is a cleaner, nice sort of single score for the factor that we can use for other things? Use it in regression, use it as a predictor in a logistic regression, whatever. Being able to use that as a nice clean factor that removes the individual item error. It addresses the reliability of the items. It actually combines them together in a smart way, and it creates a score for each person that reflects that composite. And that's sort of oftentimes the goal, is to sort of create factor scores so we get a nice clean way of measuring a latent variable without having to just sort of add up things together into a composite and compound all the error and everything. All right. So I sort of skipped the top parts. 3 general goals. Like I said before, data reduction, trying to describe relationships, and try to figure out how interpretation of sort of the factors based on the item content, and then to actually test theories. I had an instructor some years ago talking about factor analysis, and I tend to believe this too, that we're sort of taught this process that you collect data early on and you sort of do this exploratory factor analysis models, and then once you find something, you sort of move to confirmatory models. And in reality, the exploratory factor analysis assumes that you know very little about the items, that you're just sort of exploring. That's why it's called exploratory factor analysis, right? It's sort of like it almost has the equivalent connotation of like a stepwise regression. Let's just sort of see what's there, what goes in and what comes out. Let's let the computer figure out for us what items seem to go together. But no one ever collects data that way. We don't develop scales by just creating hundreds of items that are seemingly unrelated and then giving them to people and seeing how they relate. We tend to generate items based on some specific content we're trying to develop. We're trying to develop a scale. We tend to create items to go together. So then why do we then use exploratory factor analysis? That really, every sort of factor model really should be confirmatory. We should start off that way. We should start off saying, look, I developed these items to measure these 3 factors. Now I'm going to try to confirm that. I think a big part of why we've gotten this tendency of doing exploratory models first, or sort of even primarily, is because they're more readily available. Programs like SPSS and other things actually do a lot of the work for you, and they're available in those programs. And the more the programs like EQS or AMIS or those kind of things have become popular, the more you see a shift to more confirmatory models, because people are getting used to doing them. So it's almost, you can make a case that there's very rarely, if ever, a true reason to do an exploratory model. You really should be doing confirmatory models. It's just the mathematics weren't there to do confirmatory. So exploratory got developed sort of first and sort of early on, and people are sort of stuck in that mindset. It's like why people still do the Barron and Kenny mediation approach, is because that's what they learned, and then they were sort of shifted out of that to do indirect testing with like Sobel tests and that kind of stuff. People just sort of hang on to what they know and what they're familiar with, and they don't sort of move on to things that make more sense. So as we talk about confirmatory models next semester, for some of you, I'll make the same claim again there, that most models, 99% of them, are really confirmatory. So you actually have a model, you have factors, you have a theory of how they go together. I don't know why this reminded me, but it's a funny story. So this sort of friend of a friend on Facebook had written a post. This just happened yesterday, and I thought it was pretty funny. He goes, if you're gonna claim that all statistics are wrong, you should at least check to see if the person you're talking to has a data science degree before you make that statement. So this person is right now working on, I think, a Master of Science in Data Science. So they were upset that this person claimed that all statistics were wrong, and because the person, he's getting a master's in more of an expert in statistics than the person who was making the claim, he's basically saying, like, look, you don't know what you're talking about. So of course, I saw this post and I'm like, I gotta say something. So he wrote that. So my response was, because he was obviously upset, people claiming that all statistics were wrong, and I said, well, it's really more about 95% of them that are wrong. And then he went to write something back, and he ended up just posting this thing. He was like, basically just sort of admitting, yes, that's probably true. So. I found that funny, because it's true that a lot of what we do, and this is true for factor analysis, true for everything, that we're trying to make sense of the world in a very uncertain sort of way. I mean, we're trying to add some certainty in places that are uncertain. So we're trying to develop these scales, trying to develop anything, try to do logistic regression, trying to do multi-regression. We're trying to figure out how things relate, trying to find some answers. And the best we can do, and this is true, especially anything related to people, is to get close and to try to find some consistent prediction, consistent factors, consistent theories. But it's messy, and it's error prone, and it's just a pain in the ass. But that's sort of why we do it, just to try to shine even a tiny little bit of light into the darkness of sort of our understanding, even though we know that we're more likely to be wrong than right. We still sort of proceed. So his post was funny that, he was mad that someone said that all stats are wrong, but when I said that 95% of them are wrong, he was like, yeah, all right, I guess. because so there's not a big difference between 95% and 100%, but it's that 5% that is sort of what we're after most of the time. So that was kind of an interesting sort of side note digression out here. By the way, I wasn't sure if he knew what I did, and I was sort of hoping he was going to get mad at me and start to tell me about statistics and data science, just because that would have been fun. Anyway, so all right. So let's talk about. So let's get into the sort of the theory about how this stuff works. And by the way, this is true of sort of anything too. I remember probably when I was a master's student, I was probably more confident in what I was doing than I am now in terms of being certain of anything. Because when you're first, learning stuff, you feel like, oh, this is it. So the more I've learned, it's like, what's that? I think it's Socrates. The more you learn, the more you learn. The more you know, the more you know nothing. So it's like. Yeah, that's it. So the more educated you get, the more you realize, man, I don't really know anything, right? You learn there's so much more to know, and you become more uncertain about things. So I found the whole thing funny. Anyway, so let's talk about the background, where this comes from. And this is the part that's sort of highly truncated from what's in your notes. With this, I sort of talk about classical test theory, and this sort of is based on this idea. But, so the truncated version is this idea of a common factor model, and Principal Components does this too, but it does it sort of as a result. A common factor model starts with this assumption and sort of works through it. And this is the same basic idea that Cronbach's alpha has. If items are all measuring the same thing, right? You have 5 items, they all measure the same factor, they're all measuring the same construct, then there's a couple assumptions we can make. These are assumptions, but they're pretty good assumptions in terms of this tends to be true. If they are all measuring the same thing, they should all then have some part of their variability, some part of the variance that is common, that is shared, which is why this is called the common factor model, a common variance factor model, because we're trying to identify the common variance, the variance that these items share with one another. And the assumption here is the reason why the items share that variance is because that variance is being driven by the same one factor. So that's where the differences come with the arrows, and why there's this big I make a big deal about which way the arrows should go. If it's a factor analysis, we're assuming that the reason why these, let's say 3 items, the reason why these items all share variability, right, when we can find the common variance between them, is because this factor is driving their responses. If I'm depressed, I'm going to answer higher on these items. If I'm low on depression, I'm going to answer lower on these items. So my level of this metaphysical latent thing up here that we're trying to measure is driving my responses to these items. And that's why it's seen as theoretically driven, and we're trying to identify theoretically based factors. In principal components analysis, the same basic idea is there. Right? We have this thing, so we're now going to call it a component. I'm trying to identify the common variance. So what is related between these items? And because they're related, we're justifying the idea that they can be combined together into a composite. So the arrows are going this way. I'm not saying that these things are driving this. I'm saying that I can combine these together into this thing and make a composite. So it's less theoretically driven, and the results of this idea of common variance is the result of PCA, or with factor analysis, we actually start off with that as an assumption and try to refine how much common variance they share. So that's in a very overly simplistic sort of way the difference. 100% of the variability, we start off with the assumption that these items share 100% of their variability, and we only find what is common by doing the principal components analysis and identifying that sort of common variance at the end. Here we say, no, these items share variance that's far less than 100%. Let's start off with that as an assumption. theorize that this thing is driving responses and try to find how these items sort of share variance based on this assumption. Right? So that's a bit of a theoretical difference between how they work. So what does this do? How does this work in a very overly simplistic, non-technical way as I can sort of do it? It does this by trying to identify the common variance. All right. So if I can identify the common variance, that means that any variance that an item has that is not common, that is not shared with other items, isn't related to the thing you're trying to measure. So we oftentimes call it unique variance. So each item has two parts. It has the part that's this h squared here, that's called the common variance, and we have a part that is called the unique variance. So this is the part that an item shares with other items. This is the part that items don't share. This is the shared part. This is sort of the selfish part, right? The part that, like, it's like, nope, this is only my variance. I don't share this with anybody else, right? Common, shared. Those two together add up to the total variance for that one item. So the item shares some of its variance, and some of its variance is unique. The thing to keep in mind is we often refer to this thing, and I do this all the time. I often will refer to this thing as error. And that's fine, but truly, this thing is a combination of error plus something we call specific variance. Specific variance. So specific variance is variance that is in the item. It's not error. It's not noise, but it's just variance that doesn't relate to the other items. It's variance that's just specific to that item. The weight loss or eating differences question in a depression scale is a very good example of that. So it's very likely that that item is going to have three parts to its variance. There's a part that it shares with other depression items, right? That means it's because it's being driven by depression. There's also a part that's being driven by other things, like I'm fat and I went on a diet, right? Or I don't know, it's vacation and I'm eating more than I usually do, right? There's other things that are driving changes in eating habits and weight loss that aren't depression. So that's something that's specific to that item. It's not related to depression. And then there's also noise, because every item that we measure has some kind of error variability to it. So both of those errors go into the unique part, something that's called the uniqueness of the item. So this is both specific and error combined. It's just that these two together, right, we can't tell them apart. Using this model, all I know is I can identify what's common, and I can identify what isn't common, and I know that there's both specific and error variance in here, but I can't pull those two apart. So we just call that the unique variance, and we leave it alone. It's just that often people refer to this as error, and really it's more than that. It's error plus just specific variance or unshared, non-shared variance for that item. Another way of sort of thinking about this is like we have the variance of the item, you have the common variance that it shares with other people, or not other people, other items. There's the variance that's specific to the item, plus sort of random noise, random error at the bottom, at the end there. Both of those combine together into this thing we call the unique variance, often referred to as the uniqueness. And then so the common variance, the common variability is it is referred to as the commonality or communality. This is the item's commonality, this h squared, and then this is the item's uniqueness, the u squared. All that matters is we've able to identify both specific and error variance from here, and we're able to remove it so that when we actually go to combine items together, we can actually use weights to try to maximize the communality, the common variance across the items to add them together, and it gets rid of the error. We get cleaner, nicer, neater sort of composites by getting rid of all that stuff and only using the part that actually is related, that's shared, that's common. That's why it's called the common factor model, the common variance factor model. We're trying to identify the common or shared variance, separate that from unique variance, and we're going to use this common variance as an illustration of how the factor is impacting or predicting all the items. The more common variance there is, the more the factor is influencing all the items, the stronger the loading should be. Okay? So we could think of we're used to taking predictors like multiple x's, like individual items, and trying to predict some outcome with it. So when we think about composites, we usually think about composites in a way that's something like, x1, b1 x1 plus b2 x2, plus some, intercept value equals some y predicted. That's what we're used to. Or y predicted is a measured variable. These things are all measured variables, and we can sort of combine these items together to create, to predict this, right? This is creating, in a way, a sort of smart composite. It combines all the x's together and relates them to y. So now this is what it says: regression, canonical correlation, especially correlation, not correlatio, correlation flipped. So we're actually instead of trying to predict an individual item, take a bunch of items and predict an item with it. We're now taking the factors, these unmeasurable latent things, and predicting the items from it. So here's an item number 1, and I want to predict that with some kind of factor, some kind of thing, some kind of weight. Actually says loading here, but really this would be like the factor weights, similar to the canonical correlation weight or the canonical correlation coefficient, right? We want to weight those by the factors across as many factors as we need. This could be weight 1 times factor 1, weight 2 times factor 2, how many factors we need to predict this one item, plus whatever's empty, whatever is not empty, whatever is error, whatever is sort of not related, so that this part here corresponds to that common variance. This is the part that's related to the factor, and then this u squared part is whatever's left that's not predicted by the factor, which makes this the unique variance. So even though it's saying it's error here, this is the uniqueness, the part of this item that doesn't relate to any of the factors. Okay? So this psi thing represents the relationship between the factor and the item. I have loading here, but it really should be weight or coefficient to be technical. Fj is some factor, something like depression that we think predicts this item. And then this error value here is the uniqueness, the part of the item that isn't related to the factor. Again, it's under this assumption that if the factor is predicting all the items, the factor should be explaining the shared variation among the factors. So the variance that's shared among items is also the variance that's being predicted by the factor. So that's an assumption being made about how items and factors relate. All right. What's the big problem there, though? Well, first let's talk about this picture. So in both of them I have six items. In this one I'm saying, look, I can explain all 6 of those items with one factor. That factor has these weights. So I'm going to take and multiply f times this thing to give me my x1. And this error out here is the uniqueness. This is the part of x1 that is not related to f1, the factor. Right? Notice the arrow is going this way. The f drives x1, and the part of the variability in x1 that f1 explains is the commonality, is the part that actually is common between all the items. All right. So again, same thing. We're saying that there's 5 weights that are where f1 is driving all 5 of the items. You have the shared variability is really relates to these sort of weights times a factor, and then all the e's out here are the unique variances of each item. The variance that isn't shared between the items, or it's just either specific to the item or it's just random noise. This one, same 6 items, but here I'm saying that, well, okay, really I need 2 different factors. So factor 1 explains the first 3 items. Those 3 items are common, so have common variance that's explained by factor 1, and this one explained by factor 2. In this particular case, there's no arrow, no double-headed arrow or anything here, so it's actually saying that f1 and f2 are independent of one another. and there's no cross-loading. So these items only load on factor 1. These items only load on factor 2. And like factor 1 does not predict x4, and so far they're separate. And this is this is a single, or sometimes called a unidimensional model. Right? There's only one dimension needed to explain these 6 items. This one would be a 2-factor or bidimensional, or whatever you want to call it, model where it has 2 different factors explaining the same 6 items. And the way that the commonality can be estimated this way is, again, it's a measure of how much each item is explained by the factors, and therefore it's a measure of how much items relate to each other. So it's both of those things simultaneously. So the commonality for each item can be calculated by taking and just squaring and summing up the loadings. So in this case, because there's no cross-loadings, meaning that there's no item that has both factors predicting it, the commonality for, say, item number 1 would be just taking Psy524 and squaring it. So it's really just taking the loading, squaring it, and then that's our that would be the commonality for x1. This should sound familiar. When we did the redundancy analysis for canonical correlation, we took and squared the loadings and added them up, divided by whatever, to get an average shared variation. This is just doing it individually. This is the you can get a commonality for just x1, a commonality for just x2, and the reason why in this slide there's a sum is because let's say for this one it actually went from, there was a loading that went to x4 there, like that. So this would then need to be a Psy524, right? So x4 has two different factors predicting it. So if I wanted to get the commonality for the 4th item there, for x4, oh, you can't even see it. If I wanted to get the commonality h squared for the x4 variable, I would have to take Psy524 and square it, plus Psy524 and square it to get it. Right? Because there's 2 factors predicting it, I need to actually square and add up both of those to really understand what the total commonality is for x4. Right? Because that's why there's a sum. If there's only one factor predicting an item, then you just square that one loading. That's it. But here I got to square for each item across across the factors for each item. That's why there's both a J and a K there. But it was sometimes, like for item 1 would be you can't see it either. For item 1, like item 1, and item 2, this is a real loading for item 1 factor 2. This is 0, right? Because there is no loading from item 1 to factor 2 to item 1. Like this arrow from here to there, this is essentially 0, right? So when we go to sum, square, and add up across the factors, these are essentially 0. So that's why you just ignore it, because there's not a loading for factor 2 to item 1. All right, so that's what. Oh, there will likely be cross loadings. We want to try to avoid them, but even so, it depends on how you're looking at this, right? Because if this is from a confirmatory factor model, this is literally 0. In exploratory factor model, they won't be 0; they'll just be small. And if you want to get the full commonality, you really need to still take the small loading from factor 2 to item 1 and include it to really get its commonality. So in exploratory, they're almost never going to be completely 0 or missing. They're just going to be small and therefore ignorable. Tabach and Fadel give some guidelines where if a loading is below, I think, 0.3, you can essentially ignore it. Treat it like as if it is 0. But if you're trying to compute the commonality, that loading that's below 3 still needs to be computed to get the commonality accurate. And we'll see more of that in a little bit. All right, so far so good. The whole goal of this is to identify factors that try to explain the common variance between the items. So we can actually try to identify the common variance that items share. We can say that that's being driven by the factors. We can set that up. We can figure out the loadings. We can square and sum the loadings to get an estimate of what the commonality for each item is. Right? We talk about all that stuff. But there's one big question, one big issue there. Well, how do I predict a thing like x1 from a factor if the factor doesn't exist? The whole point of this was we're trying to identify factors. So how do I take a thing that doesn't exist and then use that to predict an item that does exist? Right? It seems like, what? That doesn't make any sense. So how do we predict items from factors we can't measure? This is where the mathematics comes in. So long story short, it's the same process we did before. Eigenvalue decomposition. We used eigenvector, eigenvalue decomposition that we used in canonical correlation. It's just in canonical correlation, we did some steps to make a special matrix. Remember, we took the correlation matrix, the x, y, y, x, y, and y, x, all those components, and we divided and did all this stuff to create this special matrix. We're not doing that. We're going to apply the eigenvalue, eigenvector deconstruction to the full covariance matrix. And each vector in space, so again, think multidimensional space, right? Big multidimensional space. Each vector that gets sort of projected out into space is now a stand-in for the factor, right? Because it's going to be projected through the points in space that explains the most variance. So it's trying to say, okay, well, where is there variability that's being shared amongst a bunch of items? It projects that vector into space, and then computes the eigenvalue around that, the amount of explained variance. Well, that vector in space is now going to stand in. It's going to be a proxy. It's going to be a stand-in for the factor. And we can see, okay, well, how much are items related to that vector? And we can start to figure out things like their loadings and the commonalities and that kind of stuff. So in a sense, the common factor model really could be thought of as the eigenvector model. So that's what we're doing, using eigenvectors, projecting the space. But that's where things change a little bit, is that because we're just spitting them out in the space and in any old place that sort of explains variance, and all of them seem to be orthogonal to each other, there was this process of rotation to try to actually make the factors make a little bit more sense and try to align a little bit better into where items should go. And we'll talk about that in a little bit too. But that's what we're going to do. We're going to use the eigenvalue decomposition. It's going to identify the number of vectors. We can then make choices about the number of vectors that need to be retained. Like how many vectors do we actually need to keep in order to explain a good portion of variance. We're going to let those stand in for the factors. We can compute the weights. We can compute loadings. We can then use all that to then compute the commonality and try to figure out how much variation in each item is these sort of vectors, these factors of explaining. That's really what happens. We take that, apply that to the full correlation matrix, and it actually helps to identify the number of patterns that go through. Now, if I have 24 items, the eigenvector, eigenvalue decomposition can identify up to 24 vectors. Right? You can keep just putting vectors in there until we run out of degrees of freedom. It'll go all the way through and put in 24 different vectors, basically identifying 24 factors. If I want to explain 24 items with 24 factors, that is super boring. And it's not interesting at all. So just like with canonical correlation and other processes, I want to try to identify the few, the sort of handful that are the largest and most useful, and we'll likely end up dropping the rest of them as being sort of non-significant, non-useful, as we did in canonical correlation. Okay. We got next. All right. Questions about this big burning question before we go on to talk about some of the like jargon, the terms, what matrices are involved, and all that kind of stuff. Again, this is mostly a fairly non-technical lecture. Like, I'm not getting into a whole lot of mathematics, but I want you to understand the sort of process of how this works more than anything else. Yeah. So the question is about whether or not I'll talk more about orthogonal, oblique rotations, and yeah, that's coming up because I want you to understand sort of the extraction and deciding on number of factors things first, and then we'll go on to sort of talk about what it means to sort of rotate and whether or not you want to keep the factors independent of one another or let them relate to each other, and the sort of complexities and stuff that involve with both of those decisions. All right. So again, remember we talked about the steps are measure data. You get a bunch of subjects, you give them the scale, they take it, you collect the data, and that's where it starts. And you screen it and do that kind of stuff before going. So that's really shown in this sort of data matrix. You have 1 through n subjects. So let's say you had 1,000 subjects. That'd be 1 to 1,000. And you had 20 items. That'd go 1 to 20. So k here would be 20 if you had 20 items. So variables are the items on a scale going across the top. Subjects are the individual respondents that actually took your scale and answered those sort of k questions, which gets back at this idea too. What about missing data? Well, that becomes, again, important because if person number 1 answers 19 of the 20 questions and you leave the default in SPSS alone, that person is going to be dropped out by simply not having responded to one item. So it's good to do the missing value analysis, think about things like imputation, think about how to deal with the missing values before you get to even going to this step. So all the screening, everything else should happen here before you go to the next step, before you get it to here. This means just now that I take those 20 items or k items that I have, I'm going to create a correlation matrix with it. So the correlation matrix is going to be a variable by variable matrix, 1 through k, 1 through k. So it's going to be, if I had 20 items, it's going to be a 20 by 20 matrix, sort of like that math anxiety scale matrix I showed you earlier. It's huge, 24 columns by 24 rows of correlations between all the items. The reason why this is not meant to be crossed out. It's just it's a matrix in which you have the diagonal ones going down here, so that the top part sort of repeats on the bottom. Right. So all the correlation matrices, I just put that line down there to indicate that it's sort of a symmetric matrix in that way. Okay, so those are the correlation matrices. All the other variables that don't have that, there are not correlation matrices. They're a different form. Okay, here's the interesting part. Even though we collect this data here, we want to screen this data, make sure everything's good. One of the reasons why I say that anything that happens in a data set that affects the correlation is going to affect your factor analysis, because this is your actual data. This is the data that the computer is going to use to actually run the factor analysis, which brings a really cool, important point. If you're ever reading a paper or article, or you come across anything where people make claims about, say, a factor analysis, and they provide you with the correlation matrix in that article, you can actually plug the correlation matrix in directly and replicate their factor analysis. All you need is the correlation matrix, and you can actually see if the factor analysis they found is truly what they're reporting. You can actually test it. You can actually verify that they are telling the truth. And I guarantee you that when you put the correlation matrix in, your results will be a little different, and you won't know why, because it happens very often. The data is really hard to try to replicate accurately, because sometimes the information is not complete in the narrative, in the article. Anyway, so this is the data we're going to use. We're going to use the correlation matrix. Go ahead. Yes. I mean, I wasn't going to get super into it, but yeah, you know that because you did that last semester, right? You did that in Psy524. So what Jafari is talking about is in Psy524, one of the assignments that Mark and I typically have used, I think Sarah too, is that you have to do a replication project. You got to find an article that has a correlation or covariance matrix provided, and then try to replicate their model. And the reason we do this is to teach you how not to report a confirmatory factor model, that kind of stuff, because people never give you enough information. So if you want to put in the correlation matrix to do a factor analysis, I think with exploratory factor analysis, I think you can get away with putting in just the correlation matrix, but you may have to have the mean and standard deviation. I don't remember. But I know for confirmatory, you have to have the mean and standard deviation because it converts at all the covariances. But So you have to have the correlation matrix plus the mean standard deviation of all the items, and then you can replicate their model. And when you do, you always end up finding that your degrees of freedom don't match. Something's wrong because they didn't quite tell you about a thing they did in the narrative, and what you're trying to do never quite fits to what they report. And sometimes it's not their fault. Sometimes it's an editor or somebody trying to save room and cut stuff out, so bits of information get taken out of the paper, but oftentimes it's just lazy, and they don't put all the specifics in. Anyway, so once you get it to a correlation matrix like this, the eigenvalue decomposition is going to be applied to this matrix, and then that's really the sort of extraction part of it. It's going to identify all the clusters of items. It's going to bring back different vectors. But again, trying to explain 24, in this case, k items with k factors is not very interesting. We're trying to reduce. We want to try to explain as many variables with as few factors as possible. So typically, that's why it says relatively equal, sort of almost equal to, if I take the variables times the loadings on their factors. This is factors across the top. So let's say I decide there are j factors. So typically, j should be substantially less than k. That's the goal. All right, k is the number of variables we have. I want to try to extract as few j's as possible to explain the items. So if j and k were equal, you can perfectly replicate the correlation matrix, but it's super boring. So I want to try to create this reproduce matrix. So here's the matrix I'm putting in, the correlation matrix that I'm giving the program like SPSS. I need to decide on how many factors to keep, somewhere between 1 and j, preferably closer to 1 than j, right? And then I can use that matrix to reproduce the correlation matrix, and because I want to be able to reproduce this correlation matrix as good as I can with as few factors as possible. If I do that, I can take my original matrix, subtract my reproduced matrix that I just made from my factor analysis. And if I do that, I get a residual matrix. If I did a good job, if I did a perfect job, these would all be 0. There'd be nothing left. There'd be no residuals. These would all be 0 if I did a perfect job. You're not going to get all zeros. It's not going to be perfect. As I retain less factors, these are going to be more and more different from each other, and I'm going to get a larger residual matrix. And we have to make decisions about, okay, well, what is a large, small, like how big is too big when it comes to residual matrices, and try to make some decisions about how good a job we're doing in retaining only as few of factors as we can. Okay, so data matrix gets converted to correlation matrix. That's your actual data we're using for factor analysis. It's going to do the eigenvector decomposition, but we're going to decide how many of those vectors, how many of the factors we're going to retain, right? Maybe it's only 1. Maybe I think I can explain all k variables with just 1 general factor. So that would be something like this. I think I have, I have any number of items that I want to have. All right, let's say there's whatever k is, right? K. I have k items. I think all those items are predicted by 1 single factor. This is actually a pretty common model people fit. This is called a unidimensional model. And it may seem a little bit ridiculous. I have 20 items, and I've now explained 20 items with 1 factor. 1 factor explains everything. This is actually most scales that you use assume this. When you use the Beck depression inventory, you compute 1 depression score. That's because of all 20 items on the Beck depression inventory, it assumes that it is unidimensional with an A, and that all items are being driven by the same single depression construct. So even though I have 20 items, I'm assuming I just need one factor. So this is just 1. And I take that 1, multiply it by its transpose to reproduce this matrix, the original correlation matrix, and I can see how good or bad that does. Does that one factor really reproduce everything I need to know about those items and give me a very small residual matrix? Something we can actually test for and look to see if that actually does a good job. As you leave one factor and go to more factor, the factor structure becomes multi-dimensional. We're actually past that. Becomes multi-dimensional and it sort of leaves this sort of unidimensional model all that stuff. I didn't know what time it was. You guys need to let me know. I'll just keep rambling on and on. So wait, this class goes from 9:30 to 10:45. Yeah, so I would literally get, especially when it comes to factor analysis, I'll get into it, talk about this for 4 or 5 hours. You guys don't stop me. I love this stuff. This is one of my favorite, not just topics to talk about, but I love doing factor analysis of any sort. Exploratory, confirmatory, all this stuff is all fun. All right, so let's take a break. Obviously, we're not going to start at 11 because it's 2 minutes from now. And you'll use the restroom and stuff, and I'll be back in a few minutes, and we'll go to the lab, and you see just how fun this is. How fun and how super frustrating it is all at the same time. All right, and we'll talk about factor analysis in SPSS in a few minutes.